Alright, this video is going to be a bit different. I thought I'd actually explain why the word quantum is in quantum physics and what it actually means, because there's a lot of confusion about what it means. People think it means something to do with superposition, where particles are in multiple places at once. The idea is a little bit different from that, and to explain why the word quantum is in quantum physics, you have to start off with the essentially the birth story of quantum physics and how it came about. And this is the day light was finally quantized. But we have to start off with a little bit of history first, because in about 1815, scientist Thomas Young really cemented the idea that light is purely just a wave and nothing more. And he cemented this idea by designing an experiment, which is quite simple really. It's just a light source and then a piece of card with two slits or two holes cut into it, and then a screen behind it. And he had this idea that if light is just particles, if light is made out of particles, then essentially they're just going to fly straight through the slits in a straight line. Some of them are going to bounce off, but essentially when you look at the screen behind it, you're only going to see two little spots on the screen, because the light was shone through a card with only two holes in it. Okay, but this is the result you actually get when you do this experiment. You get what we call an interference pattern, and this is something you only get from things that are acting as waves. So only waves create interference patterns, where we have all these little spots that appear on the screen. Without getting into how interference patterns work, the idea is essentially that you only see this behavior in waves. So you can see it in like water waves in nature. Because light does the same thing, Thomas Young, the physicist, concluded that light is a wave. And this idea held for another 100 years, where it was a commonly held belief in physics that light is just a wave, nothing else. Okay, but then in 1906, scientists started investigating this effect, where if you shine light on a metal, what happens is electrons on the surface of the metal are able to absorb the energy of the wave, and they get ejected from their atom and they fly off the surface of the metal. And we're actually able to detect these electrons flying off. But so far there's no problem with the wave theory of light, because waves can carry energy. You can have a tsunami, which is a water wave, and that can wipe out a city because it essentially carries a huge amount of energy. So there's no problem yet. The problem comes a bit later. Okay, so you have your electromagnetic spectrum, and you have all different kinds of electromagnetic waves, ranging from radio waves with the lowest frequency at one end and gamma rays with the highest frequency at the other. So there's no problem so far, except when you run into this problem where you find that if you shine radio waves or microwaves on the surface of the metal, nothing happens. Nothing happens to the surface of the metal. You only get electrons flying off when you increase the frequency into the ultraviolet range or beyond to X-rays or gamma rays. So what we see is half the electromagnetic spectrum. You don't get any emission at all from the surface of the metal when you shine waves from that region of the spectrum on the metal. And you only get electron emission on the second half of the electromagnetic spectrum. And I'll show you why this is a problem with the wave theory of light. Okay, so let's imagine we build a massive radio tower just for one tiny little piece of metal. And this massive radio tower is like outputting a really high intensity beam of radio waves. It's like 10 billion watts just for like a tiny little sheet of metal. No matter how many radio waves we shine at this, absolutely nothing happens. We can't get a single electron to fly off with just radio waves. And this doesn't make sense, because if you think of how waves work in nature, you can have a wave with a very low frequency, just like radio waves, like a tsunami, because a tsunami is pretty low frequency. It only happens once every 10 years. And a tsunami is a low frequency, high intensity wave because there's a massive amount of water moving. And a tsunami obviously has a massive effect when it devastates a city or town or whatever. And then compare this to a low intensity ultraviolet light beam, maybe created by like a tiny little laser pen, and it's only a few milliwatts or something. No matter how powerful or intense the beam is, it can be a very, very weak beam of ultraviolet light, and all of a sudden electrons start flying off the surface of the metal. And this would be more like having a ripple in the pond compared to our tsunami. As soon as we have a frequency that's high enough in our electromagnetic wave, we get electrons flying off, and it's nothing to do with the intensity. So this is a massive problem to the wave theory. And this was until 1906, when a man explained what was actually happening to the world. So he came up with this idea that the electromagnetic wave, or all electromagnetic waves, are made up of discrete, quantized energy packets. Okay, now discrete just means individual energy packets, and quantized means that each energy packet has a fixed amount of energy within the packet. So if we've got, let's imagine this as a radio wave. So we would find that a radio wave might have, let's say, 1 unit of energy per packet that's being transmitted along the wave. Okay, and the person who kind of introduced this idea, he calls these energy packets photons. So this is going to get into like what photons actually are. And yeah, the man's name was Albert Einstein.
Oh my God, it's Albert Einstein! It's Albert Einstein! Oh my God, it's Albert Einstein! Oh my God! Dude, you're Albert Einstein!
I'm sorry, what do you want?
You're Albert Einstein!
Okay.
Einstein, oh my God, man!
Yep. Okay, so this is what's actually going on with our big radio tower, and where we're saying it's outputting billions of watts. It's a very high intensity wave. Well, it just means it's sending out many, many millions of these energy packets. Well, in fact, trillions and trillions of these energy packets, which are also called photons. Okay? It turns out that an electron needs a certain amount of energy to be ejected from the shell. I mean, this kind of makes sense. But what happens is an electron can only absorb 1 packet or 1 photon at a time. When the electron absorbs a photon with too little energy, like a radio wave which is shone onto it, the electron basically absorbs the photon and momentarily stores that energy. But because it's not enough energy for the electron to do anything with it, in the same instant, the electron is forced to just get rid of the energy again. And what the electron does is it re-emits the photon in the same direction. So it emits another identical photon in the same direction. And then with our example of a tiny little ultraviolet light laser pen, which might only be a few milliwatts, well, it's all about how much energy there is per photon, or how much energy there is per energy packet. Now we've got more than the 10 energy units required to eject the electron from the shell. So the bar fills up, if you like, and the electron has enough energy to actually leave. And you'll notice 20 units of energy was sent in. So all the excess energy, so some energy is used to eject the electron from a shell, and the excess energy just contributes to the electron's kinetic energy. And this is really the point. Unfortunately, electrons can only absorb 1 photon at a time. The simple reason for this is that 2 photons can't be in the same point in space at the same point in time. Essentially, if it's the same radio wave and it's 2 photons in the same wave, then 1 photon is going to arrive at the electron, and then the electron is basically just going to re-emit the identical photon and lose the energy before the next photon comes in. And it always happens like this. So yeah, just to finish on something interesting, like a lot of people often look at things in quantum physics and try to construct an argument that the universe might be a simulation, because I guess if you imagine that the universe is running on a server with a specified update rate, let's say it's like a 60 ticks per second server, so it updates 60 times per second, and then you also have this rule in place that electrons can only absorb 1 photon per tick. If there is like an update like rate to the universe, like it would quite nicely explain like why electrons can never absorb multiple photons in the same instant in time. But yeah, the whole point of quantum mechanics is that it indicates that many things in the universe are quantized. So the energy of photons, or the energy of light, is quantized into discrete energy packets which are located in space along the light wave. Similarly, electron energy levels are also quantized into discrete energy values. And yes, some people argue that this implies that there's a digital nature to the universe at the fundamental level, rather than it being analog. And analog means a system can take any value from 0 to infinity, or 0 to 100, whereas digital means it can only take select values. Things can only be like a 1 or a 0, for example. But yeah, there is no actual evidence that the universe does have an update rate. I should throw that out there. But still interesting nonetheless. I mean, science and philosophy is ultimately intertwined with each other. And a lot of scientific concepts do lead into philosophical debates, and you can pick up pieces of scientific evidence to make all sorts of arguments in philosophy. But yeah, here we go. So modern physicists kind of believe in something called the wave-particle duality of light, that is both a wave and is kind of made up of particles at the same time. So what they're talking about is that sometimes light acts like a wave, sometimes it acts like a particle, and we use the photon model. Basically, we like pick and choose between the two models, depending on what like you're actually describing when it comes to like investigating how light's working. But yeah, there you go. So the word quantum in quantum physics is to do with the quantization of light, which happened in 1906, and it was Albert Einstein who birthed the whole field of quantum physics. And one of the biggest problems in modern physics right now is actually to quantize gravity and kind of make it agree with the rest of quantum theory, where we quantized electromagnetic radiation and electric fields and magnetic fields. With gravity, we know that gravitational waves exist, and gravity kind of actually can act as a wave. We detected gravitational waves in 2011, but we've yet to discover and find the graviton, the same way we've managed to discover that light consists of discrete energy packets we call photons. Some physicists ran the numbers, and they concluded that the device we would have to construct to generate these gravitational waves that are big enough to measure a graviton or detect a graviton, the device would be so like massive, it was condensed down on itself into a black hole. And the problem with black holes is information and light can't escape from it, which means the results of the experiment can't escape from it. And therefore it might just mean that some things in the universe are truly unknowable. I'm light years away. It's been 1,000 days since the signs that came from celestial planes.
of the lives that were saved. If you could live with the pain from destruction that came, running through metal veins. I feel the stars change, it's written out across my face. It transcends our mistakes in cosmic haze. They look down in disdain at what we became, constructing our own chains. I'm light years away. It's been 1,000 days since the signs that came from the celestial planes of the lives that were saved. If you could live with the pain from destruction that came. The lives that came before us always seem to know more. When I think about where they left us, what was it all for? Every life lost, yet another light that's left and gone. We make our own paths and we hope they just lead home.